This is the Magnetic Fields Homework Booklet, questions 21 to 26. So in 21, the diagram shows a square coil with its plane parallel to a uniform magnetic field. You're asked to identify which of the following would induce an EMF in the coil. Now, in order to induce an EMF, there must be a change of flux linkage. So you're looking for any sign that the number of field lines going through the area has changed. That would be a change of flux linkage. You can also look for any evidence of flux cutting. So look to see if the wire cuts through the magnetic field lines. So do consider each in turn, and hopefully you will be able to picture that it is the rotation of the coil about an axis through XY that would lead to this change in flux linkage or flux cutting. So imagine an axis through this line here and the coil rotating so that this line is going down into the page and this line of the coil is coming vertically out of the page. So you can then see that this wire is cutting perpendicularly through these field lines, as is this one in the opposite direction. Next, you're told that the graph shows how magnetic flux passing through a coil changes with time. You're asked to identify which of the graphs shows how the magnitude of the induced EMF varies in the coil with time. So remember Faraday's law, and the magnitude of the induced EMF equals the rate of change of flux linkage. In other words, it must be proportional to the gradient of this graph. Here we have flux linkage and time, so the gradient of this graph is the rate of change of flux linkage. So looking at this, you can see the gradient is increasing, so the only acceptable answer is answer D. Question 23. You're told that an aircraft of wingspan 60 metres flies horizontally at a speed of 150 metres per second. The vertical component of the Earth's magnetic field in the region of the plane is 1 × 10⁻⁵ Tesla. You're asked what EMF is induced across the wingtips of the plane. Now, on your exam specification, there is the phrase, after looking at Faraday's and Lenz's law, that states applications such as a straight conductor moving in a magnetic field. Now, this aircraft wing is an example of a straight conductor moving through a magnetic field. Now, you might choose to learn the equation that in that situation, the induced EMF is equal to the flux density multiplied by the length of the conductor multiplied by its velocity. It's a fairly easy equation to remember, BLV, but you won't find it on your data sheet. I can see that this could very easily come up again on a multiple choice question, and it could make it a very quick question to answer if you knew that fact. However, if you don't know that, let me show you how that follows on from Faraday's law. So imagine a magnetic field acting into the page here, and therefore sort of through this area that I have drawn there. This is the straight conductor, in this case the wing of the aircraft, and it is moving perpendicular to the direction of the field. Now that is leading to a change of flux linkage. It's probably easier to picture it as flux cutting. The aircraft wing cuts through the field that's going into the page. However, to work out the size of the induced EMF, you need to use Faraday's law, and you need to be able to picture a change of flux linkage. So in order to do that, you need to find an area. Now you can imagine that as the wing of the plane moves forward, it sweeps out an area through which flux can flow. Now the size of that area is the area of a rectangle with a length here on one side, and the length of the other side would equal speed times time. So whatever time interval you study this wing for, it will move a distance equal to its speed times that time interval. So that means in a time interval t, the area swept out here is L times V times t. Now the induced EMF in that time interval will equal BA divided by T. So the rate of change of flux linkage. So we would have the flux density times our expression for the area divided by the time interval. And that simplifies to BLV. And you can then see, if you know that equation, this question is in fact very easy. So maybe worth learning it. Certainly be aware of its existence. Next, you are asked to consider three identical magnets, P, Q and R. They are released simultaneously from rest and they fall through the same height. P falls directly to the ground, Q falls through the centre of a conducting ring, and R falls through a ring which is identical except that it has a gap cut into it. You are asked which of the statements below is correct in terms of the sequence in which the magnets reach the ground. So this is really an application of Lenz's law. Lenz's law states that when there is an induced EMF, the direction of the induced EMF will act so as to oppose the change that caused it. So here we could have an induced EMF because a magnet is falling through a conductor, and therefore Lenz's law would apply. So considering each one in turn. With the first magnet, there is no conductor, there will be no induced EMF, so no opposition. Lenz's law doesn't apply. So magnet P will arrive first. In the second magnet Q, there will be an induced EMF in this coil. That will lead to a current flowing. The current flowing will generate a magnetic field, and that magnetic field will oppose the motion of the magnet. So that will lead to a delay in arrival of Q. So Q will arrive later than P. That leads us then to decide about R. Now, this magnet R again falls through a conductor and an EMF may be induced, but because the wire loop is incomplete, current is not able to flow. This means that no magnetic field is generated around the coil, and again there is no opposition to the motion. So P and R fall with the acceleration due to gravity and arrive together, followed a little time later by Q. Question 25. The graph shows how the magnetic flux passing through a loop of wire changes with time. What feature of the graph represents the magnitude of the induced EMF? A fairly straightforward question testing your knowledge of Faraday's law. Faraday's law states that the magnitude of the EMF is equal to the rate of change of flux linkage. Rate of change of flux linkage is clearly the the gradient of this graph. Question 26. You're told the magnetic flux threading a coil of 100 turns drops from 5 times 10 to the minus 3 Weber to 0 in a time of 0.1 seconds. You're asked to find the average induced EMF. This is a straightforward application of Faraday's law. So Faraday's law, induced EMF equals rate of change of flux linkage. So we have the number of turns multiplied by the maximum flux linkage. This changes down to 0, so this is the change in flux linkage, and we divide by the time interval, and that leads to an answer of 5.